I'm going to present an automated target segmentation and real space fast alignment method for high throughput classification and averaging of crowded cryo-electron subtomograms. So as we know, a cell can be viewed as a dynamic molecular architecture, and within such architecture, the macromolecular complexes are nanomachines that can perform a wide range of vital tasks. A fundamental question in biology is how such macromolecular complexes work together. And the recent advance of the whole cell cryo-electron tomography techniques allows us to capture the 3D electron density of macromolecular, electron density of single cells at their close to native status at about 4 nanometer resolution, which make it possible to inspect both the structure and localization information of large macromolecular complexes inside single cells in close to native conditions. So here I'm going to show you a movie, which is basically it slices across a 3D tomogram of a section of the a single cell. And basically, such a tomogram, 3D tomogram, is obtained by capturing the 2D projection images of the sample at different rotation angles and reconstructed using back projection reconstruction algorithms. So in the long term, we are interested in the structural classification and averaging of the macromolecular complexes inside such a cellular tomogram. And in such a process, the instances of the potential instances of macromolecular complexes are first extracted as subtomograms. And then these subtomograms are aligned so that the instances with the same underlying structure will align in the same orientation. And then such subtomograms can be clustered, and the subtomograms of each cluster can be then averaged to obtain a representation of the underlying macromolecular complex structure with increased resolution and improved signal-to-noise ratio. And in the same time, we may also obtain the localization information of this underlying macromolecular complexes. However, such a procedure, to achieve such a goal, there are many challenges. First, the data is very noisy and of very low resolution compared to many other structural biology imaging methods. And it also, due to the nature of the imaging process, it has missing data. And nowadays, the acquisition of such a tomogram become highly automated, and we can easily obtain large amount of these subtomograms. However, due to the nature of 3D imaging processing, it is inherently computation intensive, and in addition, the subtomograms extracted from this highly crowded cellular environment are usually contains neighbor structures that will severely affect the classification process. And good and fast alignment is the key to successful classification and averaging process. And for such alignment method, we need it to be robust to a high level of noise and also take into account of the missing data, and it needs to be fast enough for high throughput processing. And in addition, it needs to be resistant to the existence of neighbor structures due to high crowdedness. So the main contributions of this paper are as follows. First, we develop a reference-free target complex segmentation method, which automatically excludes the neighbor structures. And then we calculate a center of mass of the target complex and propose a fast alignment method that uses real space signal. And the detection of the target complex region has these 4 steps. So first, because the tomograms are very noisy, so such denoising like Gaussian smoothing must be done to reduce the effect of noise. However, too much smoothing will eliminate the image features that are useful for the segmentation. Therefore, we want to detect an optimal Gaussian smoothing scale. And suppose the background intensity of a subtomogram is adjusted to 0, and the high image intensity corresponds to high electron density, then we can often observe that our macromolecular complex structures can occupy our high image intensity region. And in the same time, the surface of the complex is surrounded by a negative intensity surface due to the nature of the electron microscopy imaging process. And the Gaussian smoothing can be defined as a convolution between the subtomogram and Gaussian function with a parameter sigma as a scale. And given a smooth subtomogram, we first find all the local minimas and calculate a surface score, which is basically the difference between the largest eigenvalue and the rest eigenvalues of the Hessian matrix that is calculated from this local minima. Then, use such a surface score, we can calculate the cumulative score and calculate area on the curve from such score. And we repeat such a procedure also on a permutated subtomogram as a control, and we try to find the optimal scale sigma that maximizes such area on the curve ratio. So after the detection of optimal scale, we find all the local maximas and perform a watershed segmentation. And then we separate all those segments that touches the negative intensity surface into 2 groups, those structural boundary segments and those background boundary segments. And then we use such separation to find out the structural segments. And then we perform a model-based clustering of the structural segments. To do such a clustering, we assume that the intensity and locations of the observation of intensity and locations of the local maxima follows a mixture of distributions where this tau is a cluster mixing probability, and the location of local maxima follows multivariate normal distribution, and also there is a probability term that is proportional to the intensity of local maxima. We use expectation maximization to optimize the parameters of this clustering, and then use the Bayesian information criterion to find out the optimal set of cluster. And this is an example from an experimental subtomogram extracted from a bacterial tomogram. And these images are all slices through a y-axis of a single subtomogram. So this is the original tomogram, and this is after the Gaussian smoothing. And we can see the target complex located around the center region of the subtomogram, and also a lot of neighbor structures. And this is from the watershed segmentation, and this is the detection of the structural segments among the watershed segmentation. And this is the selection of the, after the model-based clustering and the selection of the center clusters. And we can see that a certain amount of neighbor structures are eliminated. And by a further refinement process, we are able to detect the target complex region, which contains a ribosome complex that is consistent with the template searching result. So after detecting this target complex region, then we can calculate a center of mass that is by consider only the work source within such a region, so that this center of mass calculation is not affected by the neighbor structures. And then we based on the above outcomes, we propose a real space fast alignment method. Alignment is essentially to find the optimal rigid transforms of two subtomograms such that the overlap or similarity of these two subtomograms is maximized. To do so, we use a correlation score that is equivalent to that is proposed by Foster et al. 2008 and our previous fast alignment method in 2012. And such a correlation score is has a missing wedge correction, and also it is enables us to use faster rotational alignment as a core part to design a faster alignment method. And it achieved a higher alignment accuracy compared to our previous fast alignment method because first, not like our previous aligned method, the new method does not have a translation invariance approximation step. Therefore, it has less ambiguity, and also it tries to use the real space signal, which occupies much larger region than the Fourier space signal that used by the previous method. So in such a way, there are less interpolation errors can be generated due to in the processing process. And basically, the correlation score is a missing wedge corrected Pearson correlation. It has three rotation correlation components, and where the numerator is basically a rotation correlation between two missing wedge and segmentation masked subtomograms, which are translationally aligned according to center mass. And the denominators are essentially the variance corrected by missing wedge masks. And given such a rotation correlation, in this form, we can express each function in P and Q as using a spherical harmonic expansion, where this Y is a set of orthogonal basis functions that are defined on a unit sphere, and this C is the coefficients. Given such expansion, so a fast calculation of the rotation correlation can be done by simultaneously calculate all the correlations over all the rotation angles through fast Fourier transform of with the suitable parameterization. And after calculating the rotational correlation over all the rotational angles, we get an array of correlation. Then we can find the local maximas of the correlations, which corresponds to a small set of rotation angles. Then we use this candidate rotation angles we examine each of these rotation angles using fast translation search to get optimal alignment. So here we have performed the experiment on the simulation data, and on the subtomograms simulated using one phantom structure and also 5 macromolecular complexes. At each distortion level of the subtomogram image simulation process, we have generated 100 subtomograms containing the instances of a structure with a random rotation and translation. To simulate the crowded environment, we we add surrounding neighbor structures to a subtomogram. Overall, our segmentation target complex segmentation procedure achieved more than 90% true positive rate and less than 0.4% of false positive rate of the region detection, and the estimation of the center of mass in general has an error of less than 2 voxels. So, and then we perform pairwise alignment of subtomograms. And this is the performance plot, where this red line is corresponds to the average alignment errors of our previous method, and this black line corresponds to the alignment error of our new method, and this green region corresponds to the distortion levels where both our methods can successfully perform alignment. And this gray region corresponds to the distortion levels where both methods failed. And this yellow region corresponds to the distortion levels where our new method can achieve accurate alignment while our old method failed. In the uncrowded subtomograms, we are already able to achieve better alignment accuracy than our previous fast alignment method at high distortion levels. Most importantly, for the crowded subtomograms, our new method is highly resistant to the existence of neighbor structures in the crowded subtomograms. However, our older method fails at most situations. So in conclusion, we have proposed, the high crowdedness is one of the major obstacles for structural classification and of macromolecular complexes in whole cell tomograms. And to address this problem, we have designed an automatic reference-free target complex segmentation method on crowded subtomograms. And then we also propose a real space fast alignment method with improved accuracy. And most importantly, it achieved robustness to the existence of neighbor structures. This work represents a step toward high-throughput, reference-free structure classification and averaging of large macromolecular complexes in single cells. Okay, I would like to thank my advisor, Dr. Frank Albert, for his guidance, and my team member, Zach Fraser and Long Pei, for their help. And I would like to thank Dr. Martin Beck from EMBO for sharing with us the experimental data. And this work is supported by following grants and travel fellowship. Thank you.
Yeah, very interesting. So do we have questions? So I was curious, so to the extent that I understand the way the alignment method is done, you're kind of doing translation or rotation of the structure, but you're not really allowing for flexibility of it. Is that something that, am I correct about that? And if so, is that something that might help or hurt your algorithm?
Okay, right. The question is whether the alignment allows the flexibility of the structures. At this moment, we just do not allow flexibility. Yeah, because this is the issue. Because of the high noisy nature of the data. Yeah. So if we relax such assumptions, then the search space will be tremendously even larger. So it's even harder to obtain good averages. Yeah. Yeah.
But do you think you might improve your accuracy that way at the cost of some time?
Well, there will be a number of factors. I think primarily the limiting factor will be the data, yeah, the quality of data, the contrast and noise level of the data, yeah, will be the primary factor. Yeah. Right. So,
Other questions? Okay, well, thank you very much.
Thank you.